Swayam Prabha. Digital India. Educated India.
Good morning, good afternoon. Welcome back to these series of lectures we've been having on analysis and design of rigid pavements. We are currently in module 3 of the course, and actually this is the very last lecture of module 3. So before we proceed to today's lecture, let's just have a recap of what we've learned so far. So module 1 of this course was briefly an introduction on rigid pavements. One of the most important things we learned there was that there are basically 4 types of rigid pavements. There are a couple of others, but for the most part there are 4 types. That is JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and then we have PCP, which is pre-stressed concrete pavements. Now, among these, JRCP is very rarely used, and we are not going to discuss it in this class. PCP is not rarely used, but is used for specialized operations, for example, airport runways. And generally, pre-stressed concrete pavements are studied in, or pre-stressed concrete is studied in structural engineering. So as of yet, it's not studied very deeply in pavement engineering. So what we're left in this class is with JPCP and CRCP. By far, the most widely used type of rigid pavement is JPCP. So if you look at any random rigid pavement somewhere, high probability that's going to be a JPCP pavement. Not that CRCP is not used. You will find many examples of CRCP around the world as well. It's just that CRCP tends to be used in very specialized conditions. For example, on heavy roads with a lot of heavy traffic, that's where you'll most likely find CRCP. The main reason it's very expensive. It has very high durability and very good performance, but it's also very expensive. So in this class, we've mostly been studying JPCP. In next module, which is module 4 on mechanistic empirical design, we will have a couple of formal lectures on CRCP. But the truth is, as far as analysis is concerned, JPCP and CRCP are analyzed very similarly to each other. So all the skills and tools which you've been learning so far, which have basically been for JPCP, apply equally or almost equally to CRCP. It's only at the design stage when the two start diverging from each other. So although I've been focusing only on JPCP so far, CRCP has also been carried along the way. Now, in module 2, module 2 and 3 have been devoted to the analysis of rigid pavements. A fair question would be, why is half the class devoted to analysis of rigid pavements without even doing any design? And the answer is, the modern philosophy of design of rigid pavements is what we call iterative design. It's mechanistic empirical, but even within that, it's an iterative design procedure. So what that means is, we start with some assumptions, we start with some trial section of the pavement, we perform an analysis to calculate the performance, and then we see if the performance is adequate with respect to some allowable value. And what that allowable value is actually quite a long story, and we'll see that in subsequent lectures in module 4. But it's some allowable value. So if our performance is sufficient as compared to that allowable value, well and good. Chances are in your first trial section it's not going to be sufficient. So then what you have to do, you have to go back, you have to update your trial section, again perform an analysis, and then check whether performance is adequate or not. And this process has to keep repeating until you get a sufficiently performing trial section, which becomes your final design. So what we see here is, within one design, you have to do several or multiple times you have to perform an analysis. And this doing that then requires you to be very good at analysis. So the reason half the class has been devoted to analysis is because in order to do a good design, you have to have mastery over analysis. So when it came to analysis, we basically had 2 modules, module 2 and module 3. Module 2 was analysis using classical methods. So classical methods we defined are basically old methods. That's what classical means effectively. They are methods which were basically analytical in nature. So what they meant was, they started from a differential equation, and we learned the differential equation in question is the Sophie-Germain equation with an additional term added to take into account a Winkler foundation. That's basically the equation that defines our JPCP slabs. So the analytical solutions start by making certain assumptions about the system. Professor Harold M. Westergaard, around 100 years ago, actually came up with the first solution. And what he made a couple of assumptions, and probably the two big assumptions, there's a couple of other assumptions also, but the two big assumptions which were made is that the load of the tire or the wheel on the slab is circular. That's a big assumption, and that is not a correct assumption. That's not what we see in practice. But more stringently, he assumed that the slabs are very large in size. So what that means is that if I have a load at the interior of the slab, then the joints do not have any substantial effect on that load. Similarly, if I have a load at the edge of the slab, then the joint on which that edge is, the joint which constitutes that edge where the load is placed, that has an effect on the stresses and displacements in the slab, but the other three joints do not. They're very far away. And thirdly, if the load is placed at the corner, then the two joints which are at the corner, they affect the development of stresses and displacements in the slab. But the other two joints which are away from the that corner, that is in the diagonally opposite corner, they do not have any effect on this response of the slab. So it was with these assumptions that Westergaard came up with a series of solutions which are called the Westergaard solutions. Subsequent modifications were made. We had several solutions which were developed after that, but all of them had essentially the same principle. You make these handful of assumptions and then you get a solution which is accurate under those assumptions. That is, there is no error. However, probably the major flaw, which really showed the drawback of using Westergaard's equations, although it is still used in some parts of the world, but the biggest drawback is it tends to severely overestimate the stresses and underestimate the displacements. So if you are designing a rigid pavement using Westergaard's theory, you tend to over-design by a lot. It's because you get very unreasonable and, more importantly, very expensive pavements because you're greatly overestimating the stresses. And that's why probably around the 1990s, particularly when digital computers started coming into commercial applications or more amateurish applications, it was then that new methods were used to analyze rigid pavements. And that new method, numerical methods, in particular the finite element method, has been our topic for Module 3. So in Module 3, we were looking at analysis of rigid pavements using the finite element method. And finite element method is sort of one, but a very good one, numerical method. There are other numerical methods also. Now, within the finite element method, the reason why the finite element method has been used is because it takes a radical departure from these analytical methods. So again, the analytical methods start with certain assumptions. The assumptions may be wrong, but under the assumptions, they derive certain closed form solutions, certain formulas, and they allow you to calculate the response of the pavements without any error besides whatever error is coming from the assumptions. The finite element method goes in the opposite direction. It does not actually make the same assumptions. So the assumptions of large slab assumption, circular loading assumption, the assumption of tensionless or tension springs, etc. None of those assumptions are made in the finite element method. So we eliminate these unreasonable assumptions. Instead, we assume, or actually we formulate it in such a way that our solution is going to carry an error. So we start with the idea that we are no longer looking for an accurate solution. We are looking for a solution with an error, but with one important property. That is, as I discretize my element, I discretize my domain into a larger number of finite elements, the error eventually goes to zero. So in the finite element method, I'm not interested in getting a solution everywhere. I'm interested in getting a solution only at a discrete set of points, which I call nodes. The nodes are connected by a finite set of elements, hence the name finite element method. And once I have if I have a very large number of elements, then my error will approach zero or my error will vanish. That's the basic assumption of the finite element method. The advantage of using the finite element method then is we completely let go of the unreasonable assumptions of the analytical methods. And now we have a method which can give us more accurate solutions without those assumptions with some error, but as long as we have enough computing power, the error will be relatively small. Remember, in practice, we are okay with small errors because when we're actually constructing these pavements, we have a lot of variability on the field. There's variability of workmanship, there's variability of material, there's variability of local site conditions. We have a lot of variability, and so we don't really need a very accurate solution. We need a reasonably accurate solution, but a little bit of error is basically the same as having some variability on the field. So that And plus one additional thing, that with the finite element method, eventually what happens in the finite element method is that instead of now having one differential equation, Sophie-Germain equation or Freiberg equation, instead of having one differential equation that we have to solve, and solving differential equations is quite a complicated thing. You maybe learned it in high school, but it's not easy to do. And I don't remember how to do it for most cases. Instead of solving a differential equation and knowing how to do it, we now reduce our differential equation into a series of algebraic equations. And I don't mean 2 or 3 equations, which is what you probably studied in school or in college. When I say we reduce it to a series of algebraic equations, I'm saying we're creating a very large number of algebraic equations. Thousands, tens of thousands, lakhs of algebraic equations. We are now having to solve a very large number of equations in order to get our approximate solution. Now, that might seem challenging. After all, in high school, if you've got a 3x3 system, that was seen as a big problem, and 4x4 was seen as impossible. Now, if I ask you to solve a system of 10 lakh equations, it's basically not going to happen. But the truth is that the one more reason why the finite element method has grown so much in the last 30 years is because personal computers have proliferated in the last 30 years. Computers are very, very good at solving large system of equations. So for us, what might look like a very difficult problem, that is solving 1 lakh, 10 lakh equations, etc., is actually a fairly simple problem for a computer. There are complications, I'm not saying it's easy, but it's not too difficult for a computer to do it either. So hand in hand with the development of the finite element method in rigid pavement analysis has been the growth of computers which can aid us in this design. And so what we learned in module 3, we learned 2 things in module 3. First of all, we learned something called the MCZ element. We learned how to analyze an individual slab, but again in this case we are not looking at every point in the slab, right? In the finite element method, we don't solve every point in the slab. Instead, we discretize the slab into a series of nodes, and the nodes are connected by an element, and we only solve the solution at the nodes. What we saw that there are many ways to do this. The one we learned was the MCZ formulation. And the MCZ formulation, one element basically consists of 4 nodes, so it's a rectangular element. We had 4 nodes, and for those nodes we had 3 degrees of freedom. That is 3 unknown responses that we are trying to calculate using the finite element method. Those 3 were W, that is the transverse displacement, theta x and theta y, these are the rotations about the x axis and the rotations about the y axis respectively. So at each node we are solving for W, theta x and theta y. So we have 3 degrees of freedom per node. We have 4 nodes in the overall element, and totally we have 12 degrees of freedom. And then the physics of the system, that is the Sophie-Germain equation in this case, that is encoded using something called a stiffness matrix. And the stiffness matrix in this case, or in this case called the local stiffness matrix, it is of size 12 by 12. So for this one MCZ element, instead of trying to solve a complicated equation, we've basically reduced it to 12 linear equations that have to be solved simultaneously. And the information about that is encoded into the stiffness matrix, which is of size 12 by 12. We also learned that we can, of course, having one element per slab is not really a great assumption. You're not going to get a very accurate result. But what we learned is that we can further partition it into more elements. As we partition it into more elements, we need to assemble it. And there we make an assumption of something called local support. So please go back to the lectures. I'm not going to repeat all of it in today's class. But we make the assumption of local support, and we can assemble the local stiffness matrices into a larger banded sparse matrix called a global stiffness matrix. When we do that process of putting it together, when we do that process, then we get a larger matrix called the global stiffness matrix. We can solve for it, and then we can solve for all the nodes that we have in our global system. So that was one thing we learned. The other thing which we learned in the previous 2 lectures was on the analysis of joints. So let me take up the next slide. So it was on the analysis of joints. So we saw how we can model one slab with multiple elements. We also have another slab with multiple elements, and now the joints between them is what we wanted to model. And we saw that basically modeling the joints, it could be done analytically. That's what the Freiberg method is, which we learned in module 2. The problem with that is you are separately analyzing the slab, you are separately analyzing the joint or the dowel bar. You're not analyzing one system as a whole, and analytically it's very complicated to actually do that analysis. In the finite element method, however, as we learned, we have a stiffness matrix for each of these 8 elements. We can assemble that into a global stiffness matrix. Furthermore, we can also assume some sort of connection, some sort of interaction between these nodes, And that interaction based on the finite element method, we can convert it to another stiffness matrix. That's the stiffness matrix of an interaction. And we can also assemble that into the global stiffness matrix. So in the same stiffness matrix, we can have the physics of the individual slabs as well as the physics of the interaction between the slabs. That is really the remarkable thing about the finite element method. The ability to model multiple physics within the same system. Of course, it's approximate. So we are carrying an error. But if we try to model the coupled physics analytically, it would actually be quite a difficult problem. And as an engineer, it would probably be an intractable problem for at least for engineers. So what we saw in the last class was we saw this model. And we saw that this is basically a 4x4 stiffness matrix, which was the component Dalbar model. If you recall from the previous lecture, it was not a very pretty model in the sense the mathematics was fairly complicated. Now in module 2, not only did I show you all the analytical solutions in module 2, I also took time out to show you how to solve the equations. And I pointed out some important things, so for example, making sure you use the correct system of units, making sure you understand what numbers to use, not to forget certain roots, so it's not square root but fourth root, etc. I gave you those kind of understandings in module 2. Module 3, you might notice that I have not really solved a lot of problems. And perhaps one hint of that is when we saw the previous lecture on the component Dalbar model, it was pretty complicated. If you had to do all the mathematics, it would get pretty overwhelming very quickly for you as well as for me. The truth is, in practice with the finite element method, we don't bother. We don't actually bother solving these systems by hand. And you don't actually learn the finite element method by solving it by hand. You learn it by programming it on a computer. And therefore, everything that we've learned, the MCZ element, the component Dalbar model, it is possible, and indeed it has already been done, to program these into a computer program. So you as a user just have to provide a small set of inputs, and we'll see some of those inputs today. You have to provide a small set of inputs, and the program will solve it for you, and then you can do any post-processing you want from the program. So today's lecture, I'm going to show you probably the best known program which is exclusively used for JPCP pavements. I'll talk about other programs also which could be used, but this is the one which is best used for JPCP. This program is called ISLAB2005. And ISLAB2005 is a finite element program exclusively used for JPCP pavements. It will basically implement everything we talked about. So the MCZ element, any temperature effects, effects of various loading effects, effects of dowels in the component Dalbar model, everything has already been implemented. And I'm just going to show you how to use the program and show you one particular illustration of the finite element method, which is the convergence which I've been talking about for some time now. Okay, so we already talked about this, that basically for our JPCP, our entire formulation comes down to Kw is equal to F, where K is our global stiffness matrix, W is our vector of degrees of freedom, that's W, theta 1 and theta 2 at each node, and then F, this underbar by the way just means it's a vector, F is the external loads which are being applied. That's what it all comes down to in the finite element method. Also recall that our stiffness matrix for each plate was of size 12 by 12. The stiffness matrix of the dowels using the component Dalbar model was 4 by 4. If you start assembling all of these, so as I drew over here, that if you have a large number of elements, so here totally we have 8 elements, you have a large number of elements, you have these interactions, very quickly the number of equations that you solve is too large. And so we have to do it using some software. So what software can you use for solving finite element problems? There are actually many commercial software. Now, I have been saying this previously, I'm going to repeat it. You are not going to learn the finite element method in 2 or 3 lectures in this class on pavement engineering. FEM is a very vast field, particularly if you have a background in civil or mechanical engineering, although I recommend for everybody, but especially for civil and mechanical engineers, I do strongly recommend that you take a formal class on finite element method. You need to spend time, it's not an easy thing to learn. I'm just trying to give you the overall idea. Now, in practice, regardless of whether it's for pavement engineering or any other application in civil, mechanical and even other fields of engineering, the finite element method ultimately people use it a lot, and therefore there are a lot of programs which are available that allow you to solve finite element problems without having to know a lot of background of the finite element method. I should warn, these programs should be used with care. A computer, as many people say, is garbage in, garbage out, which means if you use these programs without fully understanding the finite element method, you will get an answer, the answer might be completely wrong. And then it's up to you to understand why the answer was wrong. The computer is not going to tell you why the answer was wrong. So it's important to have a background in the finite element method. It's important to understand what problem you're solving to do it. But in actually solving the problem, it's best to use these computer programs. So broadly, there are two types of computer programs for FEM analysis available. There's a commercial and open source. So commercial programs, probably the most famous ones are these three, which is Abacus, ANSYS and COMSOL. COMSOL tends to be used more for multi-physics sort of problems. So if you're doing temperature and electricity and joule heating and fluid motion or something of that sort, COMSOL is pretty good for that. Abacus and ANSYS tend to be more commonly used within pavement engineering, particularly since they're meant for solid mechanics problems. Especially Abacus I've seen used quite a bit, but even ANSYS can be used. So those are commercial programs. You have to pay quite a pretty penny in order to purchase the license, etc. for them. Alternatively, there are open source programs. So there are many open source programs, and my research group, we actually use most of them. So there is one very nice open source program called Calculix, which sort of has some capabilities which are similar to Abacus. So that's a standalone program by itself. You can actually, Calculix Plus, there's something with it called Pre-Pro Max. Let me write it down. These are free and open source. You can download them. This one is a very nice packaged software that allows you to do finite element analysis. You don't have to write too much computer code if you just use Calculix and Pre-Pro Max. If, however, you want to actually write computer code, which again, in my opinion, to learn finite element methods, you must be writing the computer code. There's no other way to learn FEM. But if you want to properly learn FEM, it's a good idea to use a library to write the code. So there are three popular libraries which you'll find. Two of them are for C++ and two of them are for Python. So one is a library called GetFem. GetFem is a very interesting library. It's available both in C++ and Python, and it has very large capabilities. In fact, it is possible to model even beams and plates using GetFem. There is another library called Deal2. This is used exclusively in C++, very good and very powerful library, but it cannot analyze plates and beams, at least not yet. And then in case you're not very familiar with C++, you're not comfortable with it and you prefer Python, there is another library called Scikit-FEM, which is part of the Scikit family. Perhaps you've heard of the scientific toolkit. So this Scikit family basically is Scikit-FEM is a Python library which allows you to perform finite element calculations within Python. So these are all free and open source. You can download it. It takes a little bit of practice and learning to use them. Unlike the commercial programs, the nice thing about the commercial programs is they have very nice interfaces. There are a lot of help documents. It's fairly easy to get up and running. With the open source programs, it needs some time and some practice to get up and running in using them. But once you figure them out, both of them are equally powerful. So I don't give any particular preference on them. Now, the previous programs which I discussed, whether it's the commercial or the open source ones, they are what we call general purpose FEM program. That is, you can use it to analyze a JPCP pavement. You can use it to analyze a submarine under the ocean. You can use it to analyze a satellite in space. You can use it to analyze a building, dam, etc. General purpose. They can be used for any application, which is fine. And if that's what you desire, that's also fine. For JPCP in particular, however, it has been felt in the US primarily, it has been felt that it would be nice to have a specific program that understands that we're solving for JPCP. So our geometry is fixed, the type of loading is fixed, the type of inputs, etc. Everything is fixed. We would like to have such a program that's exclusively used for JPCP analysis, which is relatively easy to set up. The problem with these general purpose programs is every time you have to solve a new problem, you have to kind of start from zero and create a brand new geometry, etc. It's a little bit tedious to do it. Whereas if the desire was felt that if there is a specific program that only handles JPCP, a lot of the overhead costs of setting up the problem are eliminated, and then you can solve many more problems in that way. So that was the idea actually as early as the 1970s, to develop specific programs which are exclusive for solving JPCPs. A lot of this work actually came out of the University of Illinois, which is my alma mater. So I'll give you a brief history and then get to the point of what we're going to do in today's lecture. So in the 1970s, Ernie Barenberg, late Ernie Barenberg now, so he was a professor at the University of Illinois, he developed a program called ISLAB. This was basically considering plate elements. So it was the MCZ elements that we talked about. He created a computer program, this was in Fortran, to solve the system of plate elements, which we talked about in this class, without consideration of temperature effects. So if you recall a couple of lectures ago, we did consider the effect of temperature, and we saw that if we have a non-linear temperature, then this can be decomposed into a constant component, a linear component, as well as some sort of a non-linear component. So we saw this in the previous lecture. Go back to the previous lecture if you want an update on it. ISLAB in the 1970s did not have the capability to analyze this. So that was a shortcoming. But you will recognize in the 1970s, it's not like computers were everywhere and everybody was learning programming. It was a very, very niche area. The computers then were very large. They would cover large rooms. In fact, they were the equivalent of what we call a supercomputer today. You would have to program your code onto something called a punch card and punch it into a machine. It was pretty tedious at that point. In that respect, the fact that ISLAB was developed, a specific program for analyzing JPCP, ISLAB, was developed in the 1970s, is really very commendable. So it remained that way for around 20 years. In the 1990s, it was felt that some new programs had to be developed, that ISLAB was getting old and there was a need to develop new programs that could first of all be faster, because computers had gotten faster and it was important to take advantage of that speed, but also to incorporate these temperature effects. By the 1990s, understanding came around that temperature effects in JPCP are actually very significant and you have a lot of error in the analysis if you don't consider them. And so a new program which was called, initially it was called ISLAB and then an update later called ISLAB2005. This ISLAB program was written, and this was written by Kazanowicz and you. This was in a company called ARA and it was work that came out of the University of Illinois. So it was, these new program was written still solving plate elements but now with consideration of temperature effects. And this was a major upgrade. To this day, ISLAB remains one of the most important tools in rigid pavement analysis. As we learn in Module 4, which is going to be on mechanistic empirical design of rigid pavements, or JPCPs in particular, as we learn there that there is a particular design method in the world, which is the AASHTO method, the AASHTO MEPDG, ISLAB is actually what forms the numerical backbone of the MEPDG analysis for JPCP. So the reason I'm spending time to learn ISLAB, besides the fact that it's very nice and it's very it's sophisticated, but it's also very simple to use. Besides that fact, it's actually used in the AASHTO MEPDG analysis guide. So it is used as of today as the modern numerical engine to do a lot of calculations for pavement design. We'll see more on that when we go into Module 4. Now, some more work has happened since then. So also in the 1990s, another program called ILSL2, this was a Kazanowicz and Racer, again at the University of Illinois. This was developed. Now this was also plate elements, so similar to ISLAB, this was also plate elements. But here they also took into account some cracking model. So basically, if you have a slab, they also took into account what happens when you have a crack which is going through the slab. So they had somewhat of a linear cracking model. A couple of assumptions here and there were made. But they had a linear cracking model just to see how a slab or a beam would behave when you had a crack going through it. So that was in the 1990s. Took much more time. Another 20-year leap was made. So everything seems to be happening in steps of 20 years. Another 20-year leap was made, and in the 2020s, a project that I was part of, and where this is an award-winning project actually, was a program called ISLAB. This was Kennebec, Sen, and Kazanowicz, and some others contributed to it after that. Here again, we developed a new program called ISLAB, which first of all used a modern computer architecture. We used a modern compiler to gain a lot of speed. And we also, so this was still based on the ISLAB formulation, that in the sense we were still doing plate elements. This program also had consideration of temperature. One interesting addition to this was consideration of early age behavior. So early on, when you just pour the concrete is still setting and therefore it's very weak, and its modulus and its strength is still being gained. So what ISLAB did is, besides all the capabilities of ISLAB, it included consideration of early age behavior, which today is also considered to be a very important aspect in rigid pavement analysis. So initial shrinkage, initial loading, etc., those are important. And if you recall, we did spend some time in the series of lectures to talk about shrinkage as well. So ISLAB can take into account those. More work is still being done and more modern tools are being developed, including in my research group. But that's what I wanted to give you as an overall overview of general purpose FEM software, commercial or open source, and then these modern FEM software which are designed specifically for analyzing rigid pavements. Okay, so let's go into this particular one, ISLAB2005. So this is what the logo looks like if you launch it. So it's an FEM program for JPCP. It is the main reason, besides the fact that it's very useful and it's very quick to run and it's very sophisticated, is that it actually forms the numerical engine behind the AASHTO Mechanistic Empirical Pavement Design Guide. We will learn a lot more about this in Module 2. Around half of Module 2, that's about a quarter of this class, is actually devoted to the AASHTO MEPDG, and the main numerical engine to do the calculations there is ISLAB. So that's why ISLAB is such an important and fundamental tool because of the numerical engine behind it. Now, one thing to keep in mind, which as a preview, ISLAB directly is not used in Ashton Pavement ME. They actually have developed something called a neural network, so developed a surrogate model based on a neural network to account for the effects of ISLAB without having to run ISLAB. We'll see more details about that, quite a bit more details about that in module 4. Alright, so let me give you an overview of what ISLAB looks like. It's a software, it's a piece of software, so therefore it has an interface, it has a window, etc. So it's no different from any other software in that respect. What I'm going to do is I'm going to show you how to solve a relatively simple problem using ISLAB and show you some of the steps in that process. So when you launch ISLAB, you basically have a screen like this. There are 3 parts. You have an overall drawing area over here, so this is the drawing area. The drawing area is actually where the graphical display of the model is going to be placed. It's actually optional to use this. As I show, there's actually a way to just use a text file directly for this. But for those who are more used to graphical interfaces, this is what ISLAB provides. So there is a drawing area which is going to show the model. It will initially it's blank, and as you build the model, it will add up over there. There is an area over here which is the status area. So this basically just says what are the different parts of the analysis that have to be specified, and as you keep analyzing them, it will basically convert these into green dots and tell you that once everything is green, you're set and you can just run the cases. And then you have a menu bar on top. So it is built on a menu bar concept. So you've got a menu bar on top and it has many different parts to it. So you can define geometry, which obviously should be the first one. Something called areas, which I'll talk about briefly later. You have to specify layers, you have to specify subgrade, joints, temperature, load, and then you can do a couple of more specifications, and finally you can run the case. So many different options are available. We'll go through them systematically. Alright, so how do we solve any case? So far we've been focusing a lot on the finite element method and the mathematical formulation, but today's lecture is meant to be a practical lecture. So how do we solve any case using ISLAB and indeed any finite element solver? So the way we do it is as follows. So any solution is basically going to consist of the following steps. First of all, you define your slab geometry. How many slabs do you have? What is the size of the slab? What is the thickness of the slab? Define the geometry first. And then define the mesh. Again, in the finite element method, we are always going to discretize our slab into a series of elements, and this discretization is called a mesh. So basically, you're defining what are the number and size of elements. That's called a mesh. So define your geometry of the slab and define the mesh. Then go on to define the layers. So ISLAB, one of the advantages of ISLAB as compared to ILISLAB, besides the temperature calculation, ISLAB does have the capability to analyze multiple layers. So you can have more than one layer. If I'm looking at the cross section, you can have more than one layer, and these layers can be bonded or they can be unbonded. We saw this before at the beginning of module 3 in the equivalent plate concept, that you can have 2 layers which are bonded or unbonded, and you can calculate what is you can solve them as an equivalent plate and then recover the solution for the original system. ISLAB can do that for up to 2 layers at a time. So ISLAB can take 2 layers, bonded or unbonded, combine them into one equivalent plate, solve it, and then return the solution for the original system. PITSLAB, which I talked about recently, which is the more modern program, can actually do any number of layers. So it has no limitation on 2 layers. It can do any number and any combination of layers, or bonded, unbonded, etc., any combination of interfaces. So once the layers are defined, an equivalent plate concept will automatically be used by the software to solve it. So you don't have to do anything for that. The next step is to define the subgrade. What exactly is the load placed on? There are several models for it, although we always just use the Winkler foundation. Then we specify the loads. The loads can be mechanical loads, which are tires, basically vehicles. You can also specify loads in terms of temperature. You can also specify loads in terms of shrinkage, but you're going to have to separately calculate the equivalent shrinkage temperature, the fictitious shrinkage temperature, which we talked about in an earlier lecture. So you will have to calculate that separately and then specify it as a temperature. Or if you're solving an actual temperature, you can just specify an actual temperature profile. With these 4 steps, the entire system has been defined. You've defined your geometry, you've discretized the geometry, you've defined your loading, you've defined your boundary conditions, which are basically the Winkler foundation. You also define the number of layers, which you can say is part of geometry. Once that's done, you simply solve. In solving, we do keep into account how long it takes to solve a system. But the nice thing about ISLAB, as we shall see, it is very, very fast. For reasons which are slightly beyond scope of this class, the ISLAB is written in such a way to get a very, very fast solution. So we have a very fast solver and it's very quick to solve. Finally, we like to visualize the solution. That's something we call post-processing. That can be done in ISLAB, but I found that in modern computers, it's not working very well. So in my research group, we just have a separate Python program that does the post-processing and visualization for us. So you post-process, visualize, and you do whatever analysis you want based on the results. All right. So I thought the best way of going through this is by doing a solved example. In the sense, I'm not going to solve it by hand. I'm going to show you how to solve this example using ISLAB. Okay, so here is the problem. Consider a single JPCP slab. So I'm getting rid of the problem of joints. So consider a single JPCP slab. Given that the slab size is 3.5 by 3.5 meters, so that's the length and the width, pretty typical of a JPCP slab, by 250 mm. So the thickness of the slab is given to be 250 mm. Now this slab, so if I draw the cross section over here, so this is 250. And this slab is on a subgrade of K value 85 megapascals, should be capital P. So we basically have a Winkler foundation, and this K value is given to be 85 megapascals per meter. So just a note over here, this should be megapascals per meter. Now, assume that it is loaded with a tire of 100 kilonewtons and a pressure of 0.7 megapascals. So we are given a tire. We don't know what the cross section is. We'll talk about that a little later. But we are basically given that it's 100 kilonewtons. That's the load. And then the pressure is 0.7 megapascals. Using ISLAB 2005, calculate the maximum displacement and tensile stress in the slab when the load is placed at the edge. So we're given the load is placed somewhere near the edge. And we're asked to calculate the maximum displacement and tensile stress in the entire slab. Okay. So now, as I said, I already pointed out that these are the basic steps that we have to do. So we'll go in this order and progressively define the problem. So we have only one, so in this case, we have only one slab. And let's assume that the one slab is going to be defined by only one element. The element is a size 3500 by 7500 millimeters. I'm choosing to specify all loads in newtons and all lengths in millimeters. It's my choice, but you do have to be unit consistent. Similar to what we saw in Westergaard's theory, you do have to be unit consistent even in ISLAB. So I'm just going to express everything in Newton and millimeters. So let's say my slab is of size 3500 by 3500 mm, 3.5 by 3.5 meters, and I'm going to discretize it into just one element. So I do that here. Basically in the x direction, I say that I have, so in the x direction, actually I should point out one slight oddity in ISLAB. There are good reasons for it. Is that this is the x-axis and this is the y-axis. That's a little bit weird. There are good reasons. Basically, right-hand rule and the thickness goes into the paper. So that's the reason for it. So this is the x-axis and this is the y-axis. So what I'm saying here in this part, in the x direction, I have two nodes. One node at 0, x is equal to 0, and one node at x is equal to 3500 mm. And then along the y direction, again, I've got two nodes. One node at y is equal to 0 and one node at y is equal to 3500. Based on this, it's going to construct a rectangular element. So it will put the additional node up here at 3500, 3500. So with that, we have defined both the geometry as well as the mesh of the slab. We haven't defined the layers, and in this case, we actually have only one layer, but we'll do that in a second. Okay, so now we go ahead and define the layers. In this case, we have only one layer. This was a layer of concrete. We are not, as with previous problems that you've seen, we are not actually given the material properties. We have to make some reasonable assumptions. Again, I'm going to use Newton and millimeters as my base units. So my elastic modulus has to be in units of Newton per mm square, which is megapascals. And so I'm going to assume my elastic modulus is 30,000 megapascals. Poisson ratio, as we previously assumed, is 0.15. So when you go into the layers tab, layer section in ISLAB, then you select that you have one layer, you start with one layer. The name doesn't matter, it's of type plate, which also doesn't matter. You specify the thickness of 250 mm, which was given in the problem. You specify that it has an elastic modulus of 30,000, you can write it like this, 3, 4. You specify a Poisson ratio of 0.15. Now in this problem, we are not actually going to do anything related to temperature. So although you do have to give an input of coefficient of thermal expansion and unit weight, neither is going to be used unless you have a temperature problem. We don't have a temperature problem, so you can put almost a random value over here. These are actually fairly correct values. Units may be off, but we just put in some values, they're not going to affect our solution. Now, if we had another layer, we could technically press this add layer button, we would get a second layer, and then it asks us what is the interface with the layer above. Obviously, it's the interface layer above. So naturally, the first layer doesn't have any interface. There's nothing above it. So for subsequent layers, you will be able to specify whether it is bonded or unbonded. In this case, we only have one layer, which is the slab on grade. So we need not press this button. We need not add any more cases. Okay, so now what we've done is we've defined our slab, we've defined the mesh, and we've defined the layers. Next, we need to define the subgrade. Now, subgrade, it was given that it is 85 megapascals per meter. Of course, we have to do a unit conversion as previously. This I've done multiple times in previous classes. So I'm not going to repeat the whole calculation. It comes down to 0.085 Newton per cubic millimeters. So that's our base system of units. I'm not going to repeat this calculation. Basically, in the subgrade tab, we select Winkler foundation. There are other types, Spring, Vlasov, Kerr. They are not generally used anymore. Generally, we always use, as a standard in pavement engineering today, we just use a Winkler foundation. So we select Winkler foundation and only one input required, which is the subgrade K, and that is 0.085 Newton per cubic meter. So put that value in. Last thing left, which is a little bit tricky, is to place the load. Now, ISLAB, one of the assumptions in ISLAB is that only rectangular loads are allowed. Now, this is strictly speaking not a necessity. It is possible to have a load which is of any random shape. There's nothing which stops us from having randomly shaped loads. It's just that ISLAB, the way it's been programmed, it assumes that the loads are rectangular in shape. I would say this is one shortcoming, the requirement of rectangular shape. It generally doesn't matter from a design level. At the level of a design, there are enough factors of safety built in that this is not too much of a problem. But nonetheless, it is a shortcoming. So ISLAB allows only rectangular loads. So we are given that we had a 100 kilonewton load and we had 0.7 megapascal pressure. So first of all, if it's a rectangular load, we have to know what is the area of the rectangle and what is the aspect ratio. All right, let's then do the calculation. We've already done this in the past, so I'm going to quickly run by it. So let's make an assumption that the footprint is square. You could argue that it need not be square, it can be rectangular, which is true. I don't know anything about the length to breadth ratio, the aspect ratio of the rectangle. So just to be safe, I'm just going to make an assumption that it's a square load. If it's a square load, I know then the pressure is basically the load divided by square of the length, and therefore my side length is going to be square root of 100 into 10 cube, that's newtons, divided by 0.7 Newton per square mm. Do the calculation and it works out to 377.96 millimeters. So basically what I have is, I have a load, let me draw it here. So I have a load which is of side roughly 380 millimeters. Now the question is, where should I place the load? The interesting way that ISLAB does to place a load is, if you have a load, so let me draw the load over here, then in addition to specifying the load, the magnitude of the load, you also have to specify a reference point, and by default it's the bottom left point. So basically you say that within the slab, where is the X location and the Y location? Again, this is X and this is Y. You specify where is the X location and where is the Y location of this bottom leftmost point of the load, and is going to place the load accordingly. Now in this process, you have to be a little careful. You cannot allow the load to go out of the slab. That is, the load has to be within your system. So for example, I said my load is approximately 380 mm. Now suppose I decide to put this point at a distance over here, let's say of 20 mm, and then my actual load is 380 mm, and similarly in this direction. What you see over here is, now my load is going outside of the system. That's a problem. That cannot be solved. And so what you have to do is, you have to be a little careful where you're placing the load, and you have to do a little bit of a calculation to figure out where exactly to place the load. It's not difficult, it can also be automated with an Excel, but you have to be a little careful. So what I've done is, I've moved the load a little bit away. I've moved this bottom left corner a little bit away. So the load is not exactly at the edge, but it's very, very close. It's within about 5 or 10 millimeters to the edge. That's usually sufficiently close enough. It's not going to make too much of a difference whether we are exactly at the edge or just about a few millimeters away from the edge. So, and you can always do it more accurately. I did it around 10 millimeters. You can go to 1 millimeter, half millimeter at the edge. That's up to you how accurate you want to be. So what we see over here is, we now have one element, which is the slab, and then the load is placed very, very close to the edge over here. So now we successfully placed the load, and now we're done. We technically can solve. What I wanted to point out is, so all this graphical interface of clicking buttons and putting loads here, this is actually optional. If you are more of a power user and you know what you're doing, ISLAB actually generates an input file. It has a format of star.in2, so it has an extension of .in2. It actually generates a text-based input file, and here is what that input file is. The input file, it has some preliminaries, not important what these are. You have the number of slabs in each direction. Here you have one slab in the x direction, one slab in the y direction, which basically means you have one slab. Number of nodes in the x direction and the y direction, and the coordinates of the nodes in the x direction and the y direction. You have number of layers, and you have some information about the layers. These numbers should seem familiar. Information about the foundation, which is the subgrade. Here again, this number should be familiar. And then pressure, which is basically the loads. And so what you're specifying is, it specifies the pressure, which is 0.7 megapascal, and it specifies the coordinates of the rectangular or square load. So this input file is generated, and technically you can modify the input file. So in my research group, for example, we tend to create one input file from a basic case, and then we write an automatic script that modifies the input file, and we are able to run millions of cases within a couple of hours of ISLAB. So this is for power users and those who are more into heavy research and doing a lot of calculations. It's useful to just have an input file and modify the input file. But you don't ever have to actually look at the input file. ISLAB can solve everything without you having to look at the input file. So once the input file is generated, you press run on the software and it runs the simulation. Now it will give you a little bit of information on how it runs. It will tell you that it's calculating the pressure, it will form the stiffness matrix, it will solve the stiffness matrix. So it's Kw is equal to F. This line K has been formed. This line K has been solved. It says stiffness matrix inversion. It's not actually inverting it. It's just solving the stiffness matrix. So you're now getting W is equal to K inverse F. Then it calculates the displacement, which is called displacement recovery. From the displacement, it calculates stresses, and problem is completed. And it gives you a timestamp for when it happened. What you'll see here is the timestamps are basically the same, which means for this problem, this one element problem, it took less than 1 second to solve. Now, if I asked you to solve a 12 by 12 system of equations by hand, you would definitely take more than 1 second. It would be quite a big problem. But as I said, for a computer, this is a very small problem. So 12 by 12 DS is a very, very small problem. It takes less than 1 second for a computer to run, and that's what we see from the ISLAB outputs as well. Now what we can do is we can visualize the solution in the form of contours. Now this again, ISLAB has inbuilt capabilities, but it's not been working very well. It's somewhat of a dated part of the program. So it's not working very well on modern computers. So in my research group, we just have a separate Python script that takes care of post-processing. So here what I have is I've got the slab, and here I'm plotting the displacement, which is in millimeters. Again, the load is placed somewhere around here. And what we see here is the displacement is a positive displacement means it's going downwards, it's going into the ground, and a negative displacement means it's being pushed upwards. The load is placed over here, so what we're seeing is that this is indeed, this part of this slab is being pushed downwards. We seem to be getting a maximum displacement up here, which is in the corner, and that may or may not be correct. Actually, most likely this is not correct, and it's because we don't have enough elements. So basically we have a solution here, we have a solution here, we don't actually have a solution between. So the interpolation is not actually accurate. But that's what we're seeing over here, and we'll see, if we see over here in this corner, we actually have a very slight negative displacement. That is, the load is actually pushed, the load over here on the corner, on the edge, is pushing this corner a little bit upwards. That's what we see over here. So that is the displacement. Similarly, we can also visualize the stress. Here again, our load is over here. So we see we have a high stress of around 0.9 megapascals at this point, and then we seem to have another stress of minus 0.3 megapascals over here. Now, this is the stress in the x direction. This is sigma xx, which I'm plotting. I can also plot sigma xy. I can also plot the shear. What does the sign of the stress indicate? That is very important, and ISLAB has a very important convention. This is something to keep in mind. A positive stress is tensile. The stress is calculated with this assumption. The positive stress is tensile, and negative stress is compressive. And generally, as we talked about earlier, for rigid pavements, we are actually only concerned with the tensile stress. The concrete is very, very strong in compression, except for the Freiberg analysis with dowel bars. With that one exception, we don't really care about the compressive stresses. We do care about the tensile stresses. And that was the logic by which the developers of ISLAB chose to set the system, set the convention, such that a positive stress indicates a tension. So what we see here is this part of the slab near the load seems to be in tension, and the part away from the slab seems to be in compression. Seems reasonable. Okay, and similarly we can visualize sigma y, more or less same idea. I'm not going to repeat what I just said. Now, one question, what would be the displacements and stresses on the top? So everything we saw so far was on the top surface of the slab. So again, the slab has a top surface and it has a bottom surface. The question is, what would the displacements and stresses on the top surface look like? I just showed you all the displacement stresses on the bottom surface. Relatively straightforward to answer. Remember, the assumption we make for these medium thick plates is that there is no shear displacement. That is, there is no shear stress or shear strain rather. There is which means that if I have a displacement at the bottom, I'll get exactly the same displacement at the top. That's what it means to say there's no transverse shear. And so this figure which I had for displacements on the bottom surface, I'm going to get exactly the same displacement on the top surface. There's no difference. As far as the stresses go, if you recall from beams, the same thing applies to slabs. The stress actually varies linearly like this, such that the tensile stress at the top is going to be equal to the compressive stress at the bottom. Numerically, it will just be an opposite sign. So now, if this is a figure which I am showing for the bottom surface, if I ask you to plot this for the top surface, it's just going to be, you just have to multiply this whole thing by -1. So it's going to be exactly the same in magnitude, it's just going to be opposite in sign. Tension will turn to compression, compression will turn to tension. And that basically again comes down to that basic assumption that there is no shear stress through the transverse shear through the cross section. That's the basic assumption that leads to this. Okay. Now, this was all fine. So we saw successfully how we can use ISLAB to implement all the complicated mathematics we learned. We saw how it can be used to solve a system of one element. One element is not particularly useful. So remember that finite element method inherently is an approximation. So our solution definitely has an error. And as we said that if I say n is the number of elements, if n tends to infinity, in practice it can't be done, it's just a large number, but if it tends to infinity, then my error epsilon tends to 0. That's what is a basic assumption in the finite element method. So realistically what we do, we don't do one element, that's never enough. We choose a large number of elements and we check how much the solution changes. Now in this case, we don't actually know the error. We don't know the exact solution. We could technically calculate it using Westergaard's theory, but let's say for now we don't know the exact solution. So we can't actually calculate the error. We can, however, calculate the change in the solution. So for example, we can calculate delta sigma, change in the stress. And then what we can see is as we increase n, we hope that delta sigma, that the change in the stress decreases, that the stress basically becomes constant as we increase the number of elements. That we say that our solution has become mesh independent, that's one word. That is, regardless of how many elements I have, as long as I have a sufficient number of elements, my solution is no longer changing. Or the more commonly used word for that is my solution has converged. That I have a convergent solution and regardless of how many more elements I put, I basically get the same answer. That answer here being stress or displacement. So here's what I did in this case. So for the same example, so exactly same problem, instead of doing one element, I already showed you the one element solution. I did it for when we have 4 elements, for when we have 49 elements, and when we have 196 elements. So I went from one element progressively to almost 200 elements. And I ran ISLAB. In all cases, it took less than 1 second to solve. So it's really a very, very fast solver. So in all cases, I decided to plot the tensile stress at the bottom, so sigma x at the bottom surface. Here is what I got for when I had 4 elements. So 4 elements basically means I put 3 nodes or 2 elements along each direction. So along the y direction, I put 3 nodes, and along the x direction, I put 3 nodes. So this is x and this is y, and that's how I got 4 elements. Here is what the normal stress looks like. I'll show you again one more time that this is what it looked like when you had only one element, that you had some kind of a peak stress over here. The load is over here, but the peak stress was over here. That seemed to be odd. You would expect the peak stress to happen where the load is placed. So that already told you something is up with the solution. Now, when we had 4 elements, now you see the load is over here and the maximum stress also seems to be coming in the same region. That's good. Similarly, this is what 49 elements looks like, this is what 196 elements looks like, and you can do as many as you want. You can see here again, the same thing is happening. The load is placed over here, so over here, and I'm getting a maximum stress over here. What you also want to notice, if I take the maximum tensile stress, which is at the edge as expected, if I take the maximum tensile stress and I plot it as a function of the number of elements, that's what I've done over here, you will see that initially, when I basically had a very small number of elements, I basically had just one element, my maximum tensile stress was around 0.75 megapascals. Then when I increase the number, tensile stress started increasing, it went to a little bit above 3 megapascals, and then eventually it decreased a little and then it started getting flat. So this is what I call my converged solution. This was my converged solution. Around 3 megapascal is what I get. Again, if the tensile strength is 4.5, this exercise we've done in the past, then 3 divided by 4.5 is significantly less than 1, and that generally should be the case that you get in a rigid pavement. So this seems like a reasonable solution. Now, what I will leave as an exercise for you to do is to actually solve the same problem using Westergaard's theory, and then try to see whether you get a similar sort of stress. The correct answer is you will actually end up getting a higher stress, because here our slab was 3.5 by 3.5 meter. Westergaard makes the assumption of much larger stress. So you will actually get somewhat higher than 3 megapascals, but you'll still get it within the same range. So I leave that as an exercise for you to do on your own. So there are many other applications. I've just shown you one example of using ISLAB. There's much more you can do with ISLAB. For example, using ISLAB, we could change the slab size. So currently I just had one slab size, but you could change the slab size. You could also change the number of slabs. I had one slab, but you could have more slabs. When you change the number of slabs, you would then have joints in between. You can model the joints with springs, as we talked from the previous, in 2 lectures back, or you could model it using dowels, using the component dowel model, which we talked about last time. You could have tensionless springs. So again, the idea is if the slab is pushing the ground, then the ground should have a reaction, that's fine. But if the slab is being pushed upwards, the ground should not be pulling it back. That's what we call a tensionless spring. That is impossible or very, very difficult, but practically speaking, for engineers, it's impossible to do analytically. ISLAB can do it without too much difficulty. And then you can also have voids in the base layer. So for example, you could have a surface layer, you could have a base layer, and you could have one area where you say there's a void, that the base layer has been eroded. Very common, and a very common reason for certain type of distresses in rigid pavements. Impossible or almost impossible to model using analytical methods, not too difficult to model using ISLAB. So it could also model something as complicated as this. So you see, ISLAB is a very versatile software. It can model a wide variety of cases. Yes, there are errors, but as long as you have sufficiently large number of elements, the error is very small, certainly small enough that we can live with it as engineers. Alright, so with that, I conclude lecture 22, where we looked at ISLAB. So I hope that with this lecture, you got a full explanation of all the mathematics we've done in module 3 on finite element method. You saw how it all comes together, how it combines to create into a nice program. It's fairly complicated mathematics. So the difference between module 2 and module 3 was, in module 2, you had very nice closed form equations. You could do it by hand, you could do it on Excel, but they all have major drawbacks in terms of the solution. With module 3 in the finite element method, the advantage was the solution is much more accurate. There is this error in it, but it's a small error. And we don't have to make a lot of the limiting assumptions that we had to make in the analytical methods. So that was one advantage. The disadvantage was the mathematics was pretty heavy. We no longer had simple, nice equations. We had a large number of equations. We had to use matrix algebra or linear algebra, etc. to solve them. Pretty complicated. But the good thing is, a lot of it has already been implemented on computer programs such as ISLAB. And you too, if you take a proper course in FEM and you learn how to use these programs, you too can start solving this without having to actually do a lot of the mathematics by hand. So really, in practice, FEM is what is used in modern pavement analysis and design. So with that, module 3 is completed, and module 4, which will begin in the next lecture. So next lecture will be lecture 23, will be the introduction to mechanistic empirical design. So finally, we'll see how all this analysis and all this mathematics, which we've done for about half the series of lectures, how it comes together to actually design a pavement, and we can finally start doing something useful, something we care about as engineers. So I will see you in the next lecture, which will be in module 4, Introduction to Mechanistic Empirical Design. Thank you.